Okay, if you'll look at your notes for molecular geometry in Unit 4, we're going to talk about part of this set of notes today, but the beginning part, when we're dealing with types of covalent bonds and all the sigma and pi bonding, molecular geometry stuff, all of that is reviewed from Chem 1. We did that last year, so you can get information from that from the Unit 9 notes and videos from pre-AP, particularly 9-4 and 9-6, when it talks about covalent bonding and it talks about molecular geometry. So you'll want to review those just as a reminder of this, but what we want to cover today is a few pages back. Go back a few pages in your notes and you'll see the page that's titled Resonance Structures and Bond Order, and that's what we want to talk about right now. Resonance structures occur when we have two or more plausible structures that can be drawn for a molecule, for a single molecule. Now, what do we mean by that? Well, let's take the carbonate ion, for instance, that our example asks us about. Carbonate is CO3 with a 2- charge. If we want to draw the structure for that, remember that we need to look up the valence electrons for each of the atoms and add those up. Carbon, remember, has 4 valence electrons, if you hopefully have a periodic chart in front of you right now. Oxygen is in group 6A, so that tells us it has 6 valence electrons, but since there are 3 of them, that's 18 total valence electrons for oxygen. And the fact that carbonate is a 2- charge tells us that we have 2 extra electrons floating around in there somewhere. So overall, in this species, we have 24 valence electrons. And remember, it is more convenient for us to do them in pairs, so we're going to talk about there being 12 pairs of electrons that we have to show a position for in these molecular structures. So let's draw CO3 2-. We're going to put carbon in the middle, the single element in the middle, the 3 oxygens around. We've used up 3 pairs of electrons, just making those attaching bonding electron pairs. So we've used up 3 pairs. Remember, the outside atoms get first dibs on the valence electrons that are left. And once they're used up, then we'll start putting them on the central atom. But outside first. So we've used up 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we've used up our valence electrons. Remind yourself why we use 6 pairs of electrons. Remember, those dashes are a pair of electrons, and the octet rule, we want to have a total of 8 valence electrons. Around most of our atoms want those 8 valence electrons. Elements from groups 1, 2, and 3A don't want extra electrons, but the rest of them do, and 8 valence electrons, octet rule is what we're looking for. Now, when we get done, we've used up our valence electrons between these oxygens, and at first glance, it may look like, okay, we worked it out evenly, we used up our valence electrons, and we're good. However, does everything that wants an octet have an octet? And the answer is no, carbon does not. Carbon's only got 3 pairs of electrons around it. And if carbon is not happy, nobody's happy. So carbon wants that octet. How is it going to get it? The only way it can is to form a multiple bond. Remember from Chem 1, the rule was if we run out of valence electrons and some atom is still not satisfied, doesn't have an octet, then we have to look at multiple bonds. Now, multiple bonds can be formed. We can think of CNOPs. This is pretty much all you're going to see double bonds or triple bonds forming between carbon, nitrogen, oxygen, phosphorus, and sulfur. CNOPs. And it needs to form between 2 out of that group. So carbon and oxygen do fall into that group, so we can form multiple bonds. So what that means is that carbon is going to force one of the oxygens to share a pair of electrons with it. Now, does it matter and which oxygen we choose? And the answer is no, it doesn't. Any of the oxygens, they're all equivalent oxygens, so it doesn't matter. Well, the minute we say it doesn't matter, it's resonance. I'm just going to put doesn't matter up here. This is a kind of a little mnemonic device to help you remember when resonance is going to occur. So we can take any of the oxygens, let's just do this one, and take a pair and force it to share it with carbon. So it's going to get rid of it here and share it with the carbon. So I'm going to rewrite that. And technically it should have brackets around it for that negative charge. But now look what the problem asked for. It said draw all the possible resonance structures for the carbonate ion. So that's not enough. We've got to show that it could form that double bond with any of the other oxygens. So we're going to need to show one structure that has a double bond forming with the top oxygen and another one showing it forming with the one on the right. All the possible resonance structures. So I'm going to draw one here. And draw one more showing it with the right oxygen, the one on the right. So those are the possible resonance structures. But when we analyze the carbonate ion, we find that we don't see two single bonds and a double bond. We don't see species that have those kind of bond lengths. What we end up seeing is that all of the bond lengths are equivalent. What evidently is happening is that this pair of electrons forming the double bond in each of these cases are what we call delocalized, and we mention it up here in the definition. And the bond, those valence electrons, delocalized is just kind of a fancy term for lost, and we don't know where we are. Delocalized means they're just moving around from bond to bond. And what we end up with is that occurring at such a rapid kind of pace, we don't get any real difference between those bonds. So we end up with a bond that is not quite long enough to be a single bond, but it's not short enough to be a double bond. It's like it's in between those two bond sizes. So we can't say that it's a first order, it has a bond order of 1 for a single bond or a bond order of 2 for a double bond. What do we call it? Well, look at our little equation up here. It says bond order is the number of bonds divided by the number of bond sites. So let's look at what happens here. If we do that, we've got a total of 1, 2, 3, 4 bonds over 1, 2, 3 bond sites. Probably need to put that together. It's not one word, it's 2. So 3 bond sites, which gives us a bond order of 4 over 3, 4/3 bond order. So it's not quite a single bond, it's not quite a double bond, it's somewhere in between. So that's what we mean by bond order, and that's what we mean by resonance. Those are resonance structures. Okay, the last thing we want to talk about then is formal charge. Formal charge is really a more realistic method for finding charges on valence on these atoms, on these ions. The use of oxidation numbers is really actually kind of artificial. It's more or less kind of a bookkeeping method for keeping track of the electrons being transferred. So when we look at formal charge, we're looking at the number of valence electrons on a free atom minus the number of valence electrons assigned in the molecule. Another thing to keep in mind is that when we get done, the sum of all the formal charges in that species has to be equal to the total charge. What do we mean by that? Okay, so let's look at this example. We want to know the formal charge on oxygen and chlorine in the perchlorate ion. So the perchlorate ion is ClO4 with a negative charge. We have 7 valence electrons for chlorine. We have 6 for each oxygen, total of 24, and it's negative, so we have 1 extra. That's going to give us 32 valence electrons. or 16 pairs. So let's draw our structure. We've got chlorine in the middle. We've got oxygens on 4 sides. We've used up 4 pairs of electrons to do that. So now we have 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And technically we should have that negative bracket with a negative after it. Let's see. You know what I did up here? I'm going to go ahead and fix it. All of these should be 2 negatives, right? Just dawned on me when I wrote that negative down that I was pretty darn sure I hadn't done that up there, and I did not. Okay, so I've got this perchlorate molecule, and I want to find out what the formal charge is on chlorine, and I want to find the formal charge on oxygen, what those are equal to. So remember, it's the free atom valence electrons minus the ones that are assigned in the molecule itself. And I want to do something up here. I want to remind everybody that each of these dashes is actually a pair of electrons. And because it's a shared pair of electrons, one of them is going to belong to the central atom and one of them is going to belong to the atom on the outside. So keep that in mind when we're counting up the ones that are assigned in the molecule. Look at chlorine, for instance. Chlorine, we already established up here that chlorine has 7 valence electrons when it's in its free state. We're going to subtract off the number that are assigned in the molecule. Now, at first glance, we might think there are 8 because it's surrounded by 8 pairs of electrons. But remember what we just drew up there. One of those shared pair of electrons belongs to chlorine and one to oxygen. So in each one of those 4 cases, chlorine only gets one of the electrons. So we really only have 4 valence electrons assigned to chlorine in that molecule, which leaves chlorine with a +3 charge. Let's do the same thing with oxygen. Oxygen, we already established up here, each oxygen in the free state has 6 valence electrons. Assigned in the molecule, we'll look over here on this right-hand side here, you'll see that oxygen has 1, 2, 3, 4, 5, 6, and then that 7th one from the shared pair. So in each case, we're subtracting off the 7 that are assigned in the molecule, and we get a -1 for the charge on oxygen. Now remember our rule. The sum of the formal charges has to be equal to the total charge. The total charge was a -1. And it looks like this is going to add up to a +2 when you take a +3 and a -1 together. But don't forget, we've got 4 oxygens in that molecule. So we're actually going to be multiplying that by 4, which gives us a -4 total oxygen formal charge. And when you add those up, you do indeed get a -1 for the overall charge, which does match the charge of the species.